Hello, in this video, we're going to talk about some basic definitions and some tools we're going to use when we do geometry in a three-dimensional space. Before we get going, you can pause the video and make sure you have a few scratch paper that you could use and maybe a calculator, because I am going to ask you to compute some things on the way. All right, let's get to it. Okay, so here's a warm-up question. Let's say you have, you're moving and you have a really awkward shaped object. Let's say you have a 20-foot pole and you want to move it to your new apartment. And the truck you rented is dimension on the cargo space of the truck is 8 feet by 8 feet by 16 feet. Okay, so the question is, are we able to fit this pole inside of this in the space that's provided? Okay, so you might first think, well, it's gonna stick out 4 feet if we lay it on the floor, but you could actually try to get something a little bit longer in there, right? So if you take the pole and lay across the floor diagonally, you could get something that's longer than 16 feet. In fact, if you look at the floor from the top, that's 16 feet and that is 8 feet. We could measure that diagonal length by using Pythagorean Theorem. So we know that a squared plus b squared is equal to c squared. So in this case, we could plug in 8 and 16 to get the c squared, or c is equal to square root of 8 squared plus 16 squared. I could type this into the calculator. And I get 17.88 feet. Which is not quite long enough to get the pole in. Okay, so that's the first thing you might try, but you could still get something longer in there, right? If you lift up the pole so that you hit the upper corner there, and then try to get this. I hope you can imagine. If you try to get the 20-foot pole across diagonally, provided you could fit everything else you need to move in other parts of the container, will that be long enough to fit the 20-foot pole? So how would we compute something like this in three-dimensional setting? Well, we could do the two-dimensional problem again, right? So what I want you to imagine is kind of look at this two-dimensional plane that cuts through the rectangular container in a diagonal way. So if we look at this diagonal rectangle, now the bottom of this blue rectangle is this length right there, 17.88 feet. Or maybe I'll write the exact length there. So that's now the length of the new rectangle. And then height of this container is also 8 feet. So that is 8 feet. And now the diagonal of this new blue rectangle is the longest piece of pole that you could fit inside of this truck. So let's see if that will do it. So we're using the Pythagorean theorem again, but this time, let's see, 8 is my A, and my B is the C we had from before. Okay. All right, so the square and the square root will cancel out. And we get C is equal to square root of 8 squared plus 8 squared plus 16 squared. So that the square and square root cancels out, and we get square root of 8 squared plus 8 squared plus 16 squared. Let's type this into the calculator. Yeah. And I get 19.59 feet. Okay. So unfortunately, it looks like the 20-foot pole doesn't fit. So it'd be nice if you were able to compute this beforehand, right? Before you rented the truck, to see if you can fit that truck, or maybe you can upgrade to the next size so you could get that in there. But here we go. So that's how we computed the longest pole that would fit in that rectangular solid container. All right. Okay, so we're going to be doing some 3D geometry. So I want to give you some terminology. So with 2D geometry, we usually work with Cartesian coordinates. So we would draw X and Y axis like this, and usually drew figures or drew lines or functions, and then did some geometry on a two-dimensional plane like this. If we're going to add dimension to that, so we're kind of drawing like a three-dimensional thing in a two-dimensional space. So there's going to be some perspective that goes on. So we're going to have to fit some third axis in here somehow. So how we usually going to draw this is going to be this way. So there's going to be x-axis that's kind of pointing at you to the left. And then y-axis that maybe points to the right side, and z-axis that kind of points upward. So this is going to be the default position I'll usually draw. But you know, like you should be able to see these coordinate axes from any angle, right? So while this is the most common perspective that I'm going to use, technically you should be able to look at it from below or behind or rotate it and so on. So I wish I could show it to you in class, but I do have like a model of a three-dimensional axis like this. So here, the X is the blue that's kind of pointing at you. And it's a little bit hard to see. The purple axis is the Y here, and Z axis is pointing upward. This is the default perspective that you're gonna look at. So this is obviously like a PVC model that we created from some hardware store. But you could imagine the axis kind of going infinitely towards this way, these three directions, right? It's just really inconvenient and impossible to have an axis that way. You could also imagine there's a negative direction as well. So although it's not represented in this model, if there's a negative x-axis that's pointing in the opposite direction back that way, the negative y direction would go this way, and negative z direction would go that way. So this is the three-dimensional axis that we're going to use. Oh, and before I go back to the notes, notice that there's actually two reasonable ways we could have made this model. So I could have made it this way, or if I take the X and Y axis, I could have flipped it. And this would have been a reasonable axis that we could have used. There might be an alternate history where maybe something like this could have happened. But the two different axes are different. No matter how you rotate, one is a mirror image of the other. To kind of prove this to you, well, what I could do is, it's kind of hard to show. Let's go back to the notes. So in this picture right here, off to the left, if you have laid the x-axis here and y-axis, and kind of, if I laid it on my screen, I don't know if you can imagine rotating it onto the screen as you watch this, then the z-axis would point at you out of the screen, coming out towards your face. If you have swapped x and y, you could still lay this, the axis x here and y here by kind of rotating it the other way. But then the z-axis will be pointing downward into the screen. I hope you are able to imagine that. So there's two different directions that z could have gone. So how do we keep straight which is which? Well, one way to determine this is what's called the right-hand rule. So what you're going to do is to take out your right hand and kind of make like a XYZ axis with your thumb, forefinger, and your middle finger. Like this. And if your x-axis is your pointer finger and your y-axis is your middle finger, then your thumb is pointing in the direction of the z-axis. Now this is what you get if you hold your right hand. If you hold your left hand, you get the other orientation that we don't use. Okay, so if you think this is kind of confusing, if the forefinger and the middle finger is difficult to determine which goes which, what you could do is you could just kind of do it with your fingers. What you could do is you could point your four fingers in the x direction and curl it towards the y direction, and your thumb will point towards the z-axis. So I want you to kind of do that on the screen. So imagine holding up your fingers towards the x-axis here, coming out of the screen towards your face, and curl your fingers in the y direction, and your thumb should be pointing up into the z direction if you're using your right hand. So that's the right hand rule. So that's how we're going to determine if the x and y axis is put on right in the PBC model. Okay. So x and y and z axis, those are called coordinate axes. Axis is a singular, and if you're talking about more than one axis, that's the plural version of axes. The coordinate planes is the plane that's spanned by two of the axes. So let me erase all of these things. Oh no, I have erased everything. Okay. If you imagine, if you're kind of looking at this model, and maybe this kind of looks like a corner of a room, maybe. Maybe there's a window here. Maybe there's a furniture here. I don't know. I'm drawing things to make you imagine that this is a three-dimensional room. The coordinate planes are floors and the walls in this picture. So x-axis and y-axis spans the floor of this room. So that's the coordinate plane, xy plane. The left-hand wall here that you see that's spanned by x-axis and the z-axis, the left wall here is going to be the xz plane. And then the yz plane is this wall that has a window on it to the right. Okay, and I've drawn it as a square, but really you should imagine this wall as going off into infinity, up that way and down this way and in all directions. Okay, so those are the coordinate planes. So walls and floors in the floor. Okay, let's talk about octants. If you kind of imagine this three-dimensional axes and then actually the coordinate planes, that divides the space into 8 pieces, kind of like in two-dimensional space. X and Y axis divides the plane into 4 quadrants. This is the first quadrant, this is the second quadrant, that's the third, and that's the fourth quadrant. So you start with the positive x-axis and kind of go counterclockwise to name the quadrants. That's a little bit more difficult to do in 3 dimensions, right? So how do we name them? Well, this is named for the first octant. So if x, y, and z are all positive, so kind of this space that's in front of you, in front of the axes, or if you imagine standing in this room, right, then you are standing on the first octant, right? So that's when x, y, z are all positive. There are 7 other octants, but there's no standard name for them. So there's no, that's the second, that's the third, that's the fourth, fifth, sixth, seventh, eighth. It's a bit hard to keep track of where is what. So we don't use those. If you wanted to actually specify which octant you want to be in, it's much better to actually specify it by kind of saying which coordinates are positive. So I might be talking about an octant where x coordinate is positive, y coordinate is negative, and z coordinate is positive, right? So if x is positive, y is negative, and z is positive. So it's this portion over here. So it's the octant that's through this left wall, right? So there's no, the first octant is obvious what to choose. The rest is not named. Okay. All right. Let's move on. Okay. So when we name a point in 3-dimensional space, we might name it something like this. So we're gonna give the name. We usually gonna use a capital letter to denote a point. So I might call a point P. And in parentheses, I might list the X, Y, and Z coordinate, looking at it from the 3-dimensional axes that we've just talked about. So 3, 7, negative 5 means, I'm gonna look at the space. Sorry, I'm gonna try to erase this. I'm such a messy. Okay, all right. So, okay, I'm going to step 3 spaces in x direction. So 1, 2, 3, starting from the origin. And then I'm going to go 7 units in the y direction. So I'm here, and I'm going to travel parallel to the y-axis. 1, 2, 3, 4, 5, 6, 7. And then I'm going to go -5. So I'm going to go in the opposite direction as the z-axis. So I'm going to go downward, down through the floor, 5 units. So 1, 2, 3, 4, 5. And that's going to be your point P. So I hope you are able to imagine that. Okay. All right. And if we had another point and we want to measure distance between kind of 2 points in 3-dimensional space, that's kind of like the warm-up problem that we've done, right? If you had a point P and point Q, we could just kind of compute what we just did. And if you kind of simplify it, basically this is what we're doing. We're looking at the difference in the coordinates for x, y, and z. And the difference in the coordinates is the difference, the length, width, and height of the rectangular box. We're going to square each of them, add them up, and then square root it. So we were able to get that by using Pythagorean theorem twice. Basically, you could do this. So when we have a distance between 2 points, we might denote it like this. We might the absolute value of the distance between 2 points, PQ. And you might draw like a line above PQ to show this is the length of the line segment between point P and point Q. So this is the distance formula. Okay. All right. So I copied over the P and Q. So I just gave a random point. I want you to compute the distance from P to Q. Try to compute the distance from the point P to the x-axis. And I want you to try computing the distance from the point P to the YZ plane. That's the right-hand wall with the window that I drew earlier. So you can pause this and try to figure these 3 problems out. Or I can show it to you right now. Okay. So trying to find the distance between points P and Q, that's straight up using the distance formula we had earlier. So PQ square root of the difference in the coordinates. So 3 minus 1 squared, 7 minus -2, so 7 plus 2 squared, and -5 minus 4 squared. Let's see, so that's 2 squared, 4 plus 9 squared, 81, plus -9 squared, so that's another 81. So square root 4 plus 81 plus 81. So that's not a clean number. Square root of 166 or 12.88. I'm just going to leave it as the exact solution here. What's a little bit more difficult is the other 2 problems. So what's the distance between the point P and the x-axis? So how do we compute something like this? So 1, 2, 3, 2, 3, 4, 5, 6, 7, 1, 2, 3. 1, 2, 3, 4, 5. Okay. The thing is that you could actually reduce this down to a two-dimensional problem. So note that while traveling from the origin to the 3 steps in the x direction, your distance to the x-axis is still 0. So walking kind of forward towards you, 3 units of space does not change the distance at all from the x-axis. What does change the distance is walking 7 away and 5 below. But that's only 2 dimensions of movement. So if you kind of imagine everything that's happening is happening in this plane. So here's the point. Everything is happening on this 2-dimensional plane where you've traveled 7 units this way and 5 units this way. We could use that Pythagorean theorem again to get that distance right here. So when you're looking at the distance from x-axis, you could just look at this plane, blue plane, which is parallel to the YZ plane. Okay. And the equation of this plane is when x is equal to 3. Okay. So you can compute the distance to the x-axis that way. I think I'm going to leave that up to you. And then to compute the distance from the YZ plane, so in this picture, let's see. Notice that when you were traveling 7 units to the right and 5 units downward, you were traveling parallel to the YZ plane. So going parallel in Y direction and parallel in the negative Z direction, that did not change the distance from the wall. The only thing that changes the distance from the YZ plane to the point you're at is the first 3 steps you took away from the YZ plane. So the distance right here is just 3, right? Because you took 3 steps away. The other parts, the 2 coordinates, does not change the distance from the YZ plane. So when you're looking at the YZ plane, you just look at the absolute value of the x coordinate. And when you're looking at the distance from the x-axis, you ignore the x coordinate and look at the part that's parallel to the YZ plane. I hope that made sense. Okay. So let's move on. So one useful equation to have is equation of a sphere, and it's kind of analogous to equation of a circle in 2 dimensions. So remember, in 2D geometry, equation of circle looked like this. An equation of sphere is very much like that, except there's one more coordinate. So equation of a sphere looks something like this. So x minus h squared plus y minus k squared plus z minus l squared equals some radius r squared. And you might you could get to this formula by looking at the distance formula, right? So we know the distance formula looks just like this. And And this formula makes sense because we're looking at all the points that are kind of equidistant from the center of the sphere, radius r. So you fix the distance from the center and you look at all the points x, y, and z. That's exactly that distance away from that center HKL. So that's how you can derive this formula. Okay, so let's do a couple of exercise problems using equations of sphere, just kind of get used to it. And also a review of a little bit of geometry and algebra at the same time. So let's say this equation is given. Find the radius and the center of this equation. 4x squared plus 4y squared plus 4z squared minus 8x plus 16y equals to 1. This does not look like the equation of sphere that's given earlier, but we can try to do some algebra to make it look like one. The first thing I'm going to do is divide everything by 4 because it looks like a lot of the coefficients are multiples of 4. So if I divide everything by 4, I get and I have to also divide the right-hand side by 4 as well. And then I'm going to look at all the x's together, y's together, and z separately. Okay. And then what I'm going to do is what's called the complete the square. So you might have learned this in your pre-calculus class. What you do is you take the coefficient here, divide by 2, and then square it. So -2 divided by 2 is -1. If I square -1, I get +1. So that's the number you're going to add and subtract. Let's do that with y's as well. So I have the coefficient 4 there. I'm going to divide that by 2, so I get 2. And then I square it. So 2 squared is 4. And that's the number I'm going to add and subtract. Okay. If I do that, this portion for the x and this portion for the y becomes a perfect square. So this becomes x minus this number divided by 2. And then there's a -1 that's left over. And here it's going to be y plus 2 squared. And -4 is left over. Okay, so now it's starting to look more and more like equation of the sphere. The only thing I have to do is bring the constants to the other side of the equation. So I have -1 and -4. I could get it to the right-hand side by adding 5 to the both sides. So 5 plus 1/4. I can get a common denominator and get 21/4. Okay, or 5.25. Okay, now this is in the form of the equation of the sphere. The center of this sphere is the coordinate 1, comma. Notice that the negative is built into the formula. So if it's plus here, it's -2 in the coordinate of the center. And z minus L part is just z squared. So that must mean the center z coordinate is 0. And the radius is going to be the square root of 21/4. So let's see, square root of 21 divided by square root of 4 is 2. Okay, so I hope that made sense. All right. I think maybe one more example problem, and then we'll finish this video. So here I want you to try to imagine what's happening. So let's say on this problem, the equation of the sphere is given. Okay. So coordinate 1, 2, 3. So this is the center. And we have a sphere of radius 4. So you try to imagine. Look, I made it 3D by shading the sphere. If you kind of look at it, this is sitting above the XY plane, at least the center is. It goes 3 units above, but the radius is 4 units. So the sphere actually dips below the floor, the XY plane. So if you imagine it, there's a cross-sectional area. I don't know if you can imagine. So the blue circle is sitting on top of the XY plane that's on the floor. So if you take the sphere and kind of cut it at the XY plane, what is the equation of that circle? Okay. So how could you compute something like this? Well, we know something about the coordinates on that cross section. So the equation of the XY plane, that's when it's at the floor. So the Z coordinate is 0. And X and Y coordinates could be anything on that floor, but Z coordinate has to be 0. So what we do is we take this equation and kind of plug it into the Z there. We know Z is equal to 0, so plug that in. So we get X minus 1 squared plus Y minus 2 squared plus 0 minus 3 squared, so that's just 9. It's 16. And if I subtract a 9 from both sides, I get 7. So equation of that circle is exactly that. So the radius of the blue circle would be square root of 7. Right? I hope that makes sense. All right, so this is where I want to end this video. I'll see you later.